Hello there. Right, I'm here in Burnaby, British Columbia, the official host of this CAP lecture. We're going to have a talk by Ben Newling over there in University of New Brunswick, which I think you can see on our Zoom screen. But first, I've got to introduce what CAP is about. And something has come up on the screen there. So first, the Canadian Association of Physicists is your voice to the country about what should be going on in universities and physics labs all over the country. It's a network of 1,700 members at the moment. They're working in educational, industrial, or research settings. They also run granting agencies. They're voicing the views of Canadian physicists to the government and international, hello, Hamish, international societies. We sponsor annual congresses, student physics conferences. There's a publication, particular to undergraduates. Undergraduates should pay attention to the undergraduate student conferences, the CUPC, the CCU Women in Physics Conference. You should consider attending, presenting research that you may have done in the summer or else or at other times. Once you also may consider the university prize exam. There are scholarships that CAP offers that you should apply for. I think it's the September deadline. There's an annual congress where we all go, where student papers have a competition particular to them. You can also become involved already. You could volunteer to be on the Student Advisory Council to CAP, and you will be directly involved with all of these activities and bringing the undergraduate view to this organization. Finally, there's no cost to be a member. Look at the CAP websites for information on how to become an undergraduate member of CAP or a graduate student member. I think that covers the reasons we're having this lecture is to encourage more undergraduate participation in research activities that are happening across Canada. So you have also been involved with choosing the speakers. And one of those choices was Dr. Ben Newling, professor at New Brunswick University since 2002. You can see his picture there. He's a crazy guy with some crazy stuff in his office. He will tell you more about that. But he's been at University of New Brunswick since 2002. I think I mentioned that. He moved from England, so he has a funny accent, which he seems to have not gotten rid of. He is, let's see, what else did he do? He has graduate students working on magnetic resonance imaging and physics education research. And he's a musician. And we're delighted to hear more about musical physics influence on musical acoustics. So Ben, I will not delay any further. Go ahead.
Thank you very much. Thank you very much for the introduction, and thank you, of course, to the CAP for letting me talk about something that I enjoy very much. I have to remember to share not just my computer screen, but also my computer sound. So I'm just clicking on that button, and that may or may not become important later on. So musical acoustics. This is not something we often touch on in the undergraduate curriculum. You'll probably have done some vibrations and waves investigations, either as part of your first year course or in a vibrations and waves course, but musical acoustics doesn't get much of a look in. As I say, I'm very grateful to the CAP for allowing me to talk about something that I enjoy, but I'll also tell you some people I talk about it with in my home institution as well. But before I do that, let me mention that I am coming to you from the traditional unceded territory of the Wolastoqiyik, the people of the Bountiful River. This is one of my favorite pictures of the Fredericton campus of the University of New Brunswick. It's taken across the Wolastoq River, which is a gorgeous river that flows down to the Bay of Fundy. The Bay of Fundy, which meets the Atlantic, is about an hour and a half's drive from me in St. John or St. Andrews. And the river flows right through the middle of Fredericton. I should mention that the land, which doesn't look like this at the moment, there's currently a snowstorm going on, so it's all covered in snow, but it is the unceded territory, unsurrendered territory of the Wolastoqiyik. And the treaties of peace and friendship, which was signed with the British Crown in the 1700s, did not gift the land. They were actually treaties about sharing the land and sharing the land between treaty people, which is an important thing to mention. While I'm acknowledging things of great import, let me acknowledge some of my colleagues. Here on this slide, which are the members of the UNB MRI Centre, I've highlighted Professor Igor Mastikin in the front row there. Igor is, I co-taught a course on acoustics with Professor Mastikin. He did the physical acoustics bit and I talked about the musical acoustics. So some of the things I'm going to talk about today are stuff that we talked about in that course and are things that he and I have discussed together. And at the back there, Amy Ray Gauthier is now a staff member in the Department of Physics at UNB, but she started out with me as an undergraduate student doing physics education research as part of her honours project, and then she became a graduate student doing an MSc and then switching into the PhD program with me, working on magnetic resonance imaging. At the end of today's talk, I'm going to show some measurements that she made of some musical acoustics phenomenon using magnetic resonance imaging. So I'm grateful to both of those good people for letting me share their ideas and their data. So this is the conclusion slide. This is what we're going to get to at the end of this talk. So when you see this again, it's all over and you can wake up. And this at the beginning and the end will signify the chance that you have to have a little nap. I'm going to claim, well, you probably knew already, I'm going to reinforce the idea that vibrations make a sound. And I'm going to talk about the specific frequencies that vibrations might have and how that plays a part in our interpretation of sound. I'm particularly interested in music, so I'm going to talk about what's the difference between a noise and a note, a musical note. And that turns out to be harmonic series. And you may have come across harmonic series in all kinds of different physics contexts. That could be in your quantum courses, it could be in your vibrations and waves courses, and probably also in your introductory physics courses. Because the brain likes to interpret harmonic series, and we'll talk about this a little bit later, a decent musical instrument has to actually produce a harmonic series of vibrations. And I'll talk about a little bit about making musical instruments do that. And the tone of a musical instrument, the actual, the timbre, or the way that a musical instrument has character and the way it sounds, is a result of the distribution of the energy of the vibrations between the members of the harmonic series. We'll talk about that a little bit later as well. I'll show you how that works in a couple of instrumental cases. I've already given the answer to this away. What makes the noise? It is vibrations, and you need a vibration, an oscillation, to cause a sound wave to happen. This is something that's often represented in our first year curriculum in a very static way, but it actually turns out to be a really interesting moving thing. And one of my favorite websites for moving things to do with sound is the website of Dan Russell, who used to be at Kettering University and then moved to Penn State, where he runs the Graduate Acoustics program. If you are interested in sound, go and have a look at some of his animations. I'm going to show some of them today. Here is, on the left-hand side, a vibrating, we'll call it a loudspeaker, for example, a vibrating speaker, which is causing air molecules to move and generating a sound wave. And I think you can probably very clearly see that something is moving from left to right. That's the disturbance in the air molecules, the compressions and the rarefactions. You've probably heard that terminology as well. So that left to right motion, though, is the transmission of energy. And one of the helpful things about this animation is if you just look at one of the cartoon air molecules, the black dots, and just follow it for a moment with your eyes, just one black dot, you'll see that the black dot doesn't really move anywhere. It just shuttles backwards and forwards. So the air molecules themselves don't move, but the disturbance, the compression when the air molecules get pushed together and the rarefaction when they get stretched apart, that disturbance does move left to right. So the wave, as with all waves, transmits some energy without, in this case, the medium needing to move at all. And that's a thing that we often forget when we're thinking about sound waves. Now, in extreme sound waves, there are some cases like acoustic streaming where the air molecules get transported as well. But for low amplitude sound waves, it's only the disturbance, the energy that gets transported. The other thing to bear in mind, and that might not be immediately obvious, and when you think about sound waves, is the amplitude of these vibrations. So the air molecules, even in a very loud sound, the air molecules actually only move through a few microns, a few 10 to the minus 6s of meters. So 50 microns is about the thickness of a human hair. So in a sound wave, even if the sound is very loud, the air molecules are not moving very fast, and yet our ears are sensitive enough to detect it, which is astonishing, actually. The physics and the physiology of acoustics is astonishing. I'd like to talk a little bit about music today. So a noise requires a vibration, but actually music has lots of other things that are part of it. Many other things, in fact. First and foremost, rhythm. So the order and the spacing in which notes are played is important. Pitch. I'll spend a little bit of time, quite a lot of time, talking about pitch today. Pitch is quite an important aspect of music. So whether a note is high or whether a note is low, physics has something to say about why that works. If you take a bunch of pitches and you do them in succession, that's a tune or a melody. If you play different pitches together at the same time, that's harmony. And music also incorporates loudness and softness, so it incorporates some dynamics. All of those things contribute to music, and thinking about them all would be too much for one short talk, so we'll just concentrate on making individual notes today. I'm also going to put up some pictures of people who are important, and if you want to play along at home, if you're in a Zoom meeting, you could type into the chat, or if you're being forced to watch this in a classroom, the correct way to play is to write the name of the person you think is in the photograph on the back of the neck of the person sitting in front of you. That way you've got a record of the correctness of your prediction. This is not a physicist. If you know the name of this person, you could write it down now. This is actually Johannes Brahms. And the thing that Johannes Brahms has in common with a lot of the physicists who are involved in some of this research is that physicists and composers of the Romantic era went in for facial hair in a big way. So although this is Johannes Brahms, this is Ludwig Boltzmann, and you can see some definite similarity in the way they presented themselves. So there will be a few instances of physics facial hair to see today, and you can see if you can identify the people who are sporting that facial hair. As I said, we'll concentrate on making individual notes today. So we're going to talk about the physics behind making a note that has a definite pitch. Firstly, and you've probably come across this idea before, a note has a definite frequency associated with it. So the vibration has to happen at a certain rate. And the units of frequency, the hertz, is in reciprocal seconds. So a vibration that happens at 100 hertz involves 100 oscillations per second. That's actually not enough, it turns out, to give the human brain the idea of a note rather than just a straight up noise. This picture, if you're playing the competition at home, you've already written down your answer to who you think this is. This is Heinrich Hertz, after whom the Hertz is named. He is most famous for demonstrating the existence of electromagnetic waves, of course, after Maxwell's theory of electromagnetism in the late 1700s. Actually, that project was suggested as his PhD project by this guy who was working with Hertz at the time. This is actually Hermann Helmholtz, who is also an important figure in the theory of sound. Hermann Helmholtz wrote this fantastic book called Sensations of Tone, which is all about hearing and how hearing works. So for a few years before his most famous discoveries, Hertz worked as a postdoctoral assistant with Helmholtz in Germany. And in honor of his discoveries of electromagnetic waves, the units of frequency are named after Hertz. But actually, that's not enough for the brain to hear a note. What the brain needs as well is a whole series of frequencies. It needs a harmonic series of frequencies. Again, play along if you recognize this face. The harmonic series, and you can probably see the mathematical relationship by looking at the frequencies I've got listed there. A harmonic series are related by integer ratios. So 65.5 times 2 is 131, 65.5 times 3 is 196.5, and so on and so forth. The first documented interest, physics interest, or mathematics interest perhaps, that we have in harmonic series is this guy on the bottom right. That's Pythagoras. Pythagoras was interested in strings. If you pluck a string and it makes a note, a monochord, he would have called it at the time. If you pluck a string and it makes a note, how does that note related to half the length of the string, or a third of the length of the string, or a quarter of the length of the string? And so the mathematics that Pythagoras was investigating there, the sound that Pythagoras was investigating there, was the same kind of frequency ratios here, the harmonic series, integer ratios of frequency. We're going to try a radical demonstration now, which may or may not work. Turn up your volumes in whatever room or computer you're in. I'm going to play you a harmonic series played with the individual notes played one after the other. So the bottom note of that series started at 65.5 hertz and finished much higher than that. If you've got any experience with musical notation, that series is represented like this. And to those of you who read music, this series of notes will be quite suggestive. You probably noticed that the notes on the left-hand side are widely spaced, and the notes on the right-hand side are very closely spaced. I'll play the tune, the notes again, and you can try and listen for that. The pitch at the beginning is widely separated. The pitch at the end is quite closely together. So in that series of notes, we add on 65.5 hertz every time. We increase the frequency by the same amount, but the brain doesn't respond in a linear way. Our sense of pitch hears those upper notes as quite close together, and it hears those lower notes as quite widely spaced. And that's quite a common theme when we talk about physiological responses to physics phenomena. They're often not exactly linear. Now, I'm cheating a little bit because those notes were played on a piano. And actually, it turns out that when you play a single note on the piano, it's actually not just one frequency. When you strike a piano key, the piano hammer hits a string, and that string vibrates at several different frequencies. And in fact, to make it sound like a note, those frequencies need to be a harmonic series. The fact that the brain listens for harmonic series leads to some rather interesting effects. One of them is that notes that are separated by certain intervals sound really special to the brain. So there are some intervals between notes that sound really cool. And that's a very physicsy thing. We don't have time to talk about that phenomenon at the moment, but we can talk about it in questions later if you want. The thing I'd like to think about just now is that the brain sometimes makes interesting choices about how to decide what the pitch of a note is. And it makes interesting choices based on a harmonic series. Now, it's difficult to do audio demonstrations over Zoom, so this may or may not work terribly well, but the good news is you can try it for yourselves at home. So I'm going to recommend a program called Audacity. I'm actually going to share my Audacity screen at the moment because I'm running Audacity in the background. There it is. And I'm going to make sure again that I'm sharing my computer audio. We'll see if this works. I am allegedly sharing my computer audio. This actually worked perfectly fine a week ago in rehearsal and was terrible this morning. But never mind. What I'm going to do is play you two notes. The top note, both are represented in blue, but the top note here is 300 hertz. So it's just a sinusoidal waveform of a frequency of 300 hertz. That is the speaker of my computer is going to oscillate 300 times in a second. The second note I'm going to play you is 450 hertz. So it's oscillating 450 times a second. And when I play them together, now you may or may not be able to hear that, but what I hear is ah. Okay, so I'm going to play it again. Ah. So my brain has made a definite choice, that is the pitch of that note. But it turns out that those two frequencies, neither of those two frequencies actually sound like ah when you play them on their own. So this is the upper frequency, the 450 hertz, which is a little bit quiet. That sounds like ooh, 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 is the actual note. And then the lower frequency, 300 hertz, sounds like ooh. So we've got two noises, ooh and ooh. But when we play them together, you actually hear ah, which is a different note altogether. And that's because the two frequencies, 300 hertz and 450 hertz, and you've probably already worked this out for yourselves, are integer multiples of 150 hertz. So they're part of a harmonic series that would include 150 hertz if I was playing 150 hertz. And what the brain hears is, because it recognizes the harmonic series, the brain hears 300 and 450, the brain automatically inserts 150. It just assumes it was there. So the pitch that you assign, ah, is actually 150 hertz. So the brain hears a note that has a frequency of 150 hertz, even though that frequency is not playing. Again, if this is working on your Zoom, you'll be able to hear this. I'll play those two notes together, and then the bottom track, I'm going to add in 150 hertz, and you really won't be able to hear a difference at all. You might hear a difference in volume, and maybe a difference in the quality of the note, but you don't hear any change in the pitch. So if I have a harmonic series, 150, 300, 450, the brain will recognize the pitch. But even if I only play you some of the frequencies from that harmonic series, even if I only play you 300 and 450, your brain still recognizes that as a harmonic series and still assumes that the note you're playing is 150 hertz. Bizarre, but true. And the brain is kind of hardwired to listen, I should say, for these harmonic series. And so if it hears any hint that you're listening to a harmonic series, it automatically makes an assignment of pitch. I'll go back to sharing the other screen again. And I will also once again check that I'm sharing my sound, which I do seem to be. Who the heck knows? Okay, so let me reiterate. Audacity, it's a free program. You can get it and you can mess around with sounds yourself. So you can listen to some of the effects there. It's a endlessly entertaining download. Okay, so we've said that in music, if we want to make a note of a definite pitch, we need to associate that note with a definite frequency, but actually the way to tell the brain that it's got a definite pitch is to play a harmonic series. And in your first year physics studies, or even in an upper year vibrations and waves course, you're probably familiar with the idea that mechanical objects, when we vibrate them, they actually turn out to have a number of preferred frequencies at which they like to vibrate. And those preferred frequencies are determined by their mechanical properties. Let me give you an example. And this is something you can also try in the comfort of your own home. If you've ever twanged a ruler on the edge of a desk, you'll have noticed that it makes a noise. The ruler is an example of a cantilevered beam, if you hold it nice and tightly to the desk. So these three cartoons show the lowest three preferred frequencies that kind of cantilevered beam likes to vibrate at. So the lowest frequency, I'll call it F, the lowest frequency is fixed at one end, and the whole beam oscillates up and down. And the whole beam oscillates up and down together. I'll come back to that in a moment. The next frequency at which that cantilevered beam likes to vibrate is fixed at one end, but the middle of the beam and the end of the beam oscillate in antiphase. So when the end is down, the middle is up. When the end is up, the middle is down. And there's one point there, about 3/4 of the way along the beam, that's labeled with a red arrow that doesn't move at all, and that's called a node. So when there's no displacement, that's called a node. And the end that's fixed is also a node, so that's also labeled by a red arrow. And then the third preferred frequency that cantilever beams like, this one that I've labeled 17.5 times F, has 3 nodes, one at the end and then 2 more along the length. Now, these displacements are vastly exaggerated so that we can see it. When you twang a ruler, it's very difficult to see all this stuff going on. But these are the lowest 3 preferred frequencies that the ruler likes to oscillate in. And we call those frequencies normal modes. In each of these normal modes, every part of the thing that's vibrating is undergoing simple harmonic motion. Some parts of it at the nodes are undergoing simple harmonic motion with an amplitude of 0, but all the other parts have non-zero amplitudes, and they're all doing simple harmonic motion, and they're all doing simple harmonic motion in a synchronized way. They don't get out of phase. So even though in the middle normal mode you can see that some parts of the beam are up when others are down, they don't get out of sync with one another. So they're always at their maximum displacement at the same time as one another. Now, it turns out, and you've probably already written down the name of this guy at the top here, it turns out that any vibration of the cantilevered beam can be written as the sum, the weighted sum, so there's a coefficient in front of each of those normal modes, the weighted sum of normal modes. And this idea that you can write some complicated occurrence as an infinite series is down to this guy. This is Fourier, Jean-Baptiste Joseph Fourier. And that's a tremendously powerful idea in musical acoustics. We'll come back to it a little bit later. But one way to represent a vibration of a cantilevered beam is by telling me how much of each of those frequencies is present in the vibration. That will turn out to be a very important idea. Now, most mechanical systems, even though they have preferred frequencies at which they like to vibrate, the preferred frequencies don't make a harmonic series. So F 6.3F, 17.5F, that's not a harmonic series, they're not integer multiples. So when you build a musical instrument, unless you're careful, you'll get something that sounds more like a noise. When you twang a ruler on the edge of the desk, you can probably discern a pitch, but it sounds mostly like a noise. If you're very careful, you can shape the cantilevered beams so that they actually do have preferred frequencies that are harmonic series. This device is called a kalimba, sometimes known as a thumb piano, and it makes a very beautiful noise. It's basically a collection of cantilevered beams. I'll show it in profile there, so you can see the beams are fixed at one end, and you twang them with your finger on the other end. But these beams are shaped, and because they've been shaped, the preferred frequencies are a harmonic series, and so they make a very definite note. And that is actually one of the things that people do in musical instrument design. So coming up with a good musical instrument often involves making sure that the vibrations that happen are a harmonic series. I'll give you an example, and I'm going to give you an example from a book by Lord Raleigh, which he finished in 1877. You don't get a point for guessing that this is Lord Raleigh. You do get a point if you know what his name was before he was Lord Raleigh. Because when he wrote this book, The Theory of Sound, which comes in 2 glorious volumes, and you can still buy from Dover Press, he was just 35 years old, and then he was called John William Strutt, and he looked like this. So the book it's a really good book. If you're interested in how things vibrate, it's really fun. It starts in a very simple way, with vibrating things that you're probably familiar with from first year physics, like a pendulum. And then it talks a little bit about how those vibrations might die away, what the mechanisms for that is. And then there's some discussion of how slightly more complicated systems vibrate. And the next thing that Lord Raleigh or William Strutt talks about is bars. So here are the diagrams from his book. On the right-hand side there, figure 31, that's his diagram for a cantilevered beam. So it's fixed at one end and it's oscillating up and down. On the left-hand page in figures 29 and 30, you can see his diagrams of how a bar that's just resting on supports vibrates. So that's a free bar. And we have quite a lot of musical instruments that consist of free bars. So glockenspiels, marimbas, these kind of things. You have a bar that they're percussion instruments. You have a bar that you strike with a mallet. I'll talk a little bit more about those later. But Raleigh spends some time talking about how the frequencies are related and whether or not they don't make a harmonic series. There are some things that are close, but they're not a harmonic series when you strike a bar and how it vibrates. Now, it turns out that Lord Raleigh's brother-in-law was in possession of a drum. So Raleigh then goes on to talk about drums in particular. Oh, here is a picture of a marimba, which is an instrument where you strike a bar. And what you do if you want to make a nice note from a marimba is that you don't just have a block of wood to strike. This would be a sort of unshaped marimba bar, just a rectangular block of wood. What you actually do with a marimba is you shape the bars like this. You carve away some of the wood, and when you do that, you make a bar that vibrates with a harmonic series, so it sounds much more like a note. And then you also have to be very careful that when you balance the bar, you don't damp out the vibrations by having the bar sit on some solid surface. You actually balance the bar at the points labeled with the red arrows there. So you balance the bar at the nodes, and then the bar can vibrate fairly freely. These two bars that I showed you are made of white maple. And this was a project from our acoustics course in third year. One of my current graduate students made these bars. White maple is quite hard to work with. It's a very hard wood. He spent hours and got lots of splinters carving out this shape. So a shout out to Mike Gill there for spending that time. Instruments that have bars to make a noise have to be carefully suspended, as I said. This chime bar is actually, all the bars are held up by string, which is wrapped around the bars. You might be able to see the black line there. And that string is carefully positioned, so it's just about at the position of those two red arrows. And that means when you strike the bar, you get a sound that rings. Whereas if you don't suspend the bar from those 2 points, you get a sound that dies away very quickly and is very disappointing, musically speaking. I'd mentioned that Lord Raleigh had a drum. We should get to the drums. So the next thing he talks about in his book is vibrations of membranes. These diagrams on the right-hand side show Raleigh's predictions for the preferred frequencies at which a circular membrane vibrates. Now, this particular circular membrane is fixed at the edges, so it's tied down at the edges. So in the top left-hand diagram, what that's supposed to represent is that the whole of this membrane, the whole of the skin of the drum, can go up and down together. So when the middle of the drum is up, all parts of the drum are up, and when the middle of the drum is down, all parts of the drum is down, and the whole skin vibrates up and down, but it's fixed at the edges. So if you can see me on the camera there, where my elbows are is where the edge is fixed, and the skin just goes up and down. The next preferred normal mode frequency is the one that I've circled in red there. That still has a node all the way around the edge, so the edge of the drum doesn't go up and down, but the two halves of the drum go up and down in antiphase. So when the top half of the drum is up, the bottom half of the drum is down, and vice versa. So the two halves of the drum go up and down oppositely. And that red line across the middle is a nodal line. So that part of the drum skin doesn't move at all. It stays fixed. And the two semicircular halves go up and down oppositely in antiphase. So we've got two nodes there in 2 dimensions on this membrane. We've got a nodal circle where the outside is fixed, and we've got a nodal line where the middle bit doesn't move. And the other preferred frequencies that Raleigh has sketched out for us show all other kinds of normal mode vibrations. So on the right-hand side, the top right, you can see one nodal circle, the outside, and 2 nodal lines across the middle. So the 4 quarters of the drum go up and down in antiphase. And then the fourth mode is really interesting. That one has one nodal circle on the outside and then another nodal circle which is smaller and inside. And that second circle doesn't move. So you end up with the outside of the drum going up when the inside of the drum goes down, and vice versa. You end up with 2 circles going up and down. I'll show you an animation of that in a few minutes because it's very beautiful to look at. And it is possible to visualize with a stroboscope, for instance. But one of the things that Raleigh points out in his theory of sound is that these preferred frequencies of oscillation of a membrane don't actually make a harmonic series. This is F, 1.59 F, 2.13 F, and so on and so forth. That's not a harmonic series. In an orchestra, what you do and this was the instrument that Lord Raleigh's brother-in-law had. In an orchestra, what you do is you actually take that membrane and you put underneath it a kettle, a container, and that looks like this. That's a kettle drum. And the kettle drum, the container underneath, holds volume of air, and it is difficult to compress or expand that volume of air. So what happens is that this very first mode of vibration, where the whole drum skin goes up and down together, that doesn't really happen because it's difficult to compress the air that's contained in the kettle. So that mode is suppressed. When a kettle drummer, when a timpanist strikes this drum, that mode doesn't really happen. The lowest frequency that happens is the one there that's labeled 3F, where the two halves of the drum skin go up and down in antiphase. And then the next one, the 4F and the 5F modes also sound. And that is now a harmonic series. So if you take a drum skin, a membrane, and you put a kettle underneath it, what would have come out as a wet thud noise if you just struck the skin on its own, because that doesn't sound a harmonic series and it doesn't sound like a note, now sounds like a well-rounded boom. It sounds like a note. So a kettle drum like this, because you've suppressed one of the modes of vibration, sounds with a definite pitch, because the ear hears 3F and 4F and 5F and 6F and says, oh, hello, there's a harmonic series going on here. I know what the pitch of that should be. Just like it did earlier on with our demonstration with Audacity. And Raleigh points all of this out in his book. Here's the animations I promised. And again, these are from Dan Russell's website. He's at Penn State, the graduate acoustics program there. The first mode at the top is the lowest frequency of a free drum skin. That's the one we suppress in the timpani. And so when we put the kettle underneath, that mode doesn't sound. And instead we get some of these other gorgeous modes instead. And a skilled drummer can change which of these modes contribute to the sound by striking the drum skin in a particular place. If you strike the drum skin at a location, there can't be a node at that location. And so it can suppress some of the modes that sound, and that can change the way that the drum sounds. If you're interested in experimenting, you can stretch a across a tube of some kind and make yourselves a balloon drum. This is just made with an ordinary party balloon, and you can experiment with the kind of noises that you get now. I'd like to talk a little bit about air in tubes as well, because that's my next favourite kind of sound making device. And I'll show you some more animations that illustrate some things that you've probably seen in an introductory physics course. If you confine air in a tube and you excite the air at one end, like I do, for instance, in the balloon drum with the drum skin, the air molecules can only move in certain ways. And only certain wavelengths of vibration actually fit exactly into the tube. Here's an example of the lowest preferred mode of vibration of a tube that's open at one end on the left-hand side and closed at the other end. And again, I'm using one of Dan Russell's cartoons of the air molecules to show you what goes on. It's important to animate these things because often in a first year textbook, you'll see a graph that is static and doesn't give you an impression of what's going on here. But the top graph is a plot of, along the horizontal axis position along the tube and along the vertical axis, the displacement of the air molecules. And because this is animated, you can see that at the left-hand side of the tube, the air molecules go back and forth. They travel through a long distance. Long is a relative term here. I've already mentioned it's only a few microns. But at the right-hand end of the tube, where the tube is closed, then the air molecules can't move back and forth, so their displacement is zero. The pressure variation inside the tube is the opposite of that. So at the left-hand side of the tube, all the air molecules move together. So there's no squishing together of the air molecules or stretching out of the air molecules. And that means that because they move together, the pressure stays the same. So you can see the left-hand end of the tube, the pressure doesn't change. On the right-hand end of the tube, where some of the molecules are trapped against the wall, the molecules get squished together. And so there's a wild fluctuation in the pressure. So what we see here is that the top graph shows a displacement node at the right-hand side of the tube, but a pressure antinode, so the biggest variation of pressure. And on the left-hand side of the tube, there is a displacement antinode, so the biggest movement of air molecules, but a pressure node, so almost no change of pressure at all. That's the lowest frequency at which the air inside a pipe likes to vibrate. We'll call that F. The next highest one, if the tube is closed at one end, is 3 times that. And just watching how the air molecules move is endlessly fascinating. And the next frequency, 5 times that. You'll already have noticed that these are parts of a harmonic series. So we've got F and 3F and 5F, just the odd numbers of a harmonic series. So the brain is perfectly happy to interpret these vibrations as a note. It hears a note of frequency F. So pipes can be used to make musical instruments. Here are some pipes in the marimba. I showed you a marimba earlier on. One of the things that marimba makers do to reinforce the sense of pitch that you get from striking the shaped bar is they hang a tube underneath. And the tube has a specific length, and you choose the length so that the preferred frequencies suggest the same note as you get from striking the bar. And of course, the length of the tube determines the frequencies. So this video shows how the length of the recorder can determine the pitch of the sound, the preferred frequency. As I cover fewer of the holes, the tube gets shorter. That's a good place to stop. As I cover few of the holes, the tube gets shorter, and so the note gets higher. But also a smaller recorder tends to be a higher pitch. Those were treble, soprano, and sopranino recorders, one after the other. So the length of the tube determines the pitch that we hear, because it determines the harmonic series that sounds. And so you can choose lengths underneath the marimba. In other wind instruments, you choose the length of the tube for the pitch of the sound you want. So bigger instruments are generally lower. And this forms a whole family of what physics calls aerophones. Now, orchestral music tends to group the families differently than physics does, but aerophones is anything where there's a vibration in a tube, a vibration of air in a tube. And physics likes to categorize these instruments by what the mechanism is for making the vibration happen. So some instruments you blow, like the recorder, you actually blow air past a sharp edge, and that causes a sound. Some you use a reed, so saxophones and clarinets, for instance, have a piece of cane. Oboes and bassoons have 2 pieces of cane. They're strapped together and they vibrate. And there's also a carugaphone. I'll come to that in a second. The reeds doesn't have to be wood that vibrates. It can sometimes be other things. So the brass family are considered to be reed instruments in physics. They're lip reeds. This video comes with a trigger warning. I'm going to set it playing. It's actually the lips of a trombone player viewed through a transparent trombone. And you can see, depending which note the trombone player plays, their lips vibrate in different ways. Beautiful, I think you'll agree. So the instrument category here is lip reed, because it's the lips that start the vibration happening, but it's the length of the trombone itself that determines what harmonic series sounds, so determines what pitch you hear. And of course, you probably know that a trombone, the length can be changed with the slide, and that means that the pitch changes when you change the length. A different harmonic series sounds for each length of trombone, but the lips oscillating, as in the video, to get the air moving. I'll go back to the recorder a second, because I did promise to show you some of Amy's MRI results. And we've done some MRI measurements in a recorder. This is how the recorder makes a sound. You blow air through a narrow tube called a flue. The air hits a sharp edge. And on the recorder, the sharp edge is just at the top here, just below the mouthpiece. And then the air fluctuates between going above that sharp edge and below that sharp edge, and it fluctuates at a preferred frequency. And then you strap the whole of that apparatus to a long tube, and of course the tube has preferred frequencies that are a harmonic series, and you hear a pitch. And it turns out that if you're doing magnetic resonance imaging, which we do at the UNB MRI Center, you can make your measurement sensitive to motion. So depending how you choose to do the MRI image, you can make the contrast in the image sensitive to motion. So what Amy did was she took a recorder like this, a soprano recorder. She strapped it in the middle of a superconducting magnet. That magnet there has a magnetic field of 2.4 Tesla, which is 50,000 times the Earth's field. And she used exactly the same magnetic resonance imaging techniques that we use in hospitals to image brains. So the physics is the same behind that technique, but Amy used it instead to image the gas that we're blowing through the recorder. So the gas here is sulfur hexafluoride, SF6. It's got 6 fluorine atoms surrounding the central sulfur, and those fluorine atoms are NMR active, so we can detect them with magnetic resonance. The recorder, here I've done a terrible thing to a recorder, so you can see the internal structure. We're not going to get any MR signal from the plastic of the recorder. We're actually going to get MR signal instead from the white spaces in the image, which are where the gas is. So that's the holes inside the recorder and outside the recorder. So here up above where it says image field of view or image FOV, that's above the recorder, and then in the middle is the inside of the recorder, and then at the bottom is below the recorder. And Amy spent a long while sat next to a magnet which was making this noise all the time with ear defenders on, so she didn't have to listen to the recorder being played for hours on end, to measure the velocities. These are the velocity maps that Amy acquired using magnetic resonance imaging. So you can see in the left-hand side, which is the horizontal component of velocity. That's the component of velocity along the length of the recorder. So I've labeled that VZ. The Z-axis is left to right as you look at it. Where this is dark red, the fluid is moving fast as it cuts past the edge and makes the noise. The flickering of the air above and below the record edge happens much faster than the time scale on which we make the MR measurements, so we get an average velocity here. So the map A shows you the speed, well, the magnitude of the Z component of velocity, left to right. The map B shows you the component Vy, and it's coloured red for upwards and blue for downwards. So Vy is the component of velocity up and down the screen as you're looking at it. So you can see there where the gas separates as it crosses the edge of the recorder. That's the mechanism that's responsible for the sound production. The fluctuation up and down is the mechanism responsible for the sound production. So this gas, SF6, is completely invisible, but we can detect it with magnetic resonance because the fluorine nuclei are NMR active. We didn't really here learn very much about how recorders work. What we did learn is the limits of the magnetic resonance technique, which is what Amy was developing. So she developed some methods for imaging turbulent flows, of which this was the sort of first step. The harmonic series that I pointed out sounds for each of these instruments has 2 characteristics. First of all, there are which frequencies are present in the harmonic series, but second of all, there's how much of each frequency is present in the harmonic series. And it turns out that, and you remember Fourier said earlier on that we can represent any vibration of the air inside my recorder as the weighted sum of those harmonic series. It turns out that the weighting of each of those frequencies determines the tone, which we call the timbre of the recorder. So here is a diagram that shows how much of each of these frequencies are present in a particular note. So there's a lot of the fundamental frequency, that's F, and there's about half of that 2F, and a little bit less 3F, 4F, 5F, 6F, and so on and so forth. So this histogram, this bar chart, is a vibration recipe. It shows you how much of each of the harmonic series is present in an oscillation. And that determines how a note sounds in terms of its character, the tone or timbre of an instrument. So if an oboe plays the same note as a recorder, your brain detects the same pitch, but those 2 notes sound qualitatively different. You would easily be able to say that's an oboe and that's a recorder. And the only reason you can do that is because of the weighting of the normal modes. One last demonstration before I finish up. I very much enjoy the website of Paul Falstad, who has done a great service to physics by sharing all of his little applets, which are very lovely. He is one that allows us to view the vibration of a bar. So this is the bar that Raleigh talked about in his book. That's the fundamental mode of the bar. It vibrates up and down. I can add in a little bit of, I can mix in different amounts of the modes. So this is the bar graph along the bottom that shows how much of each frequency is contributing. Let me put in some of the next normal mode. and some of the third normal mode. And now you can see, again, the motion is enormously exaggerated, so the bar doesn't really move this much. But you can see that each of these three normal modes is now contributing, and I can determine how much of these modes are contributing by choosing the height of the histogram bars. The human ear is sensitive to how much of these there are, but it's not sensitive to the phase. So as far as the ear is concerned, having the second mode in antiphase is exactly the same as having all three modes in phase. That would sound the same to you. But the amount of each of those modes is actually what determines how the bar sounds, the quality, the tone, the timbre of its tone when you strike the bar. And so a skilled marimba player, for instance, who has a bar like this to hit, will choose where to hit the bar in order to excite which possible mixture of modes, which will determine exactly how the bar sounds as you mix more and more in. So the ear and our brain doesn't hear the shape of the bar. Our brain hears this mixture of different components and makes a decision about how the sound, the pitch of the sound, and it makes a decision on the quality of the sound based on what that bar graph looks like. Last change of summary. I'm going back to the slideshow just to conclude by getting back to the conclusion slide. I mentioned right at the beginning, you need a vibration to make a sound. Vibrations have a specific frequency, but our brain tries to identify families of frequencies. Our brain listens for harmonic series in order to decide pitch. And a decent musical instrument needs to produce a family of vibrations that form a harmonic series. And so when you shape a marimba bar, or when you build a kalimba, what you do is try and make sure that the sound is a family of frequencies, so that your brain will, first of all, detect a note, and second of all, identify a particular quality. And that's probably enough for today. Thank you.
Thank you very much, Ben. We do have some questions from the chat. First one, I think I read somewhere that the human ear is insensitive to possible phase shifts in the different frequency components of sound. Is this true?
Absolutely true. And that was the thing I was demonstrating there at the end with the applet from Paul Falstad. The ear doesn't really hear, for one note from a single source, the ear doesn't hear any phase difference. So if you mix together a bunch of different vibrations, the relative phase of those doesn't matter at all. It's only the amount of each one that matters. Now, when phase becomes important is if you have two sources. So if you have a stereo system, if the different phase between those two sources, the ear can detect, and it can make a big difference. And also when you have two sources with very similar frequencies, the ear is fabulous at detecting beats, which you've probably come across in a first year or a second year physics course as well. So in those cases where you've got two sources, the ear is great at detecting phase, mostly because the phase has an effect upon the amplitude. But when you've got a single source with a mixture of frequencies, absolutely, the ear doesn't notice phase.
Thank you. Next question I have from the chat, and I welcome anyone to continue sending questions into the chat. How do normal modes of vibration relate to the resonance frequencies in musical instruments, and how does this affect the sound they produce?
So can you just do that first bit again?
How do normal modes of vibration relate to the resonance frequencies in musical instruments, and how does this affect the sound they produce?
Yeah, the normal modes are the resonant frequencies, but basically, so if you excite a system at a particular normal mode frequency, you mostly get a resonance. So they're exactly coincident for most systems. And when you want to make a musical instrument, what you do is change the mechanical properties of the instrument so that those normal modes are a harmonic series.
Perfect, thank you. And I have one last question from the chat, unless anyone else wants to join in. In musical instruments, how do harmonics affect the quality of sound produced, and how does this relate to the fundamental frequency of the note being played?
Brilliant. So the fundamental frequency is the lowest preferred frequency that your mechanical system will vibrate at. The mixture of how much of that fundamental frequency and how much of all your higher frequencies you have is exactly what gives the tone, which we call the timbre of the instrument. So it's exactly what gives the quality of the sound. So if you hear two different people singing the same note, you can tell who's singing because they have a different mixture of the amounts of the harmonic series in each of those sounds. So it's that quality, that difference between two different people or between two different kinds of instrument is entirely based on how much of each of those frequencies is present. I hope that answers that.
Okay, and another one in the chat. In your example of the ear interpretation of simultaneous 300 hertz and 450 hertz sounds, does the brain always interpret the fundamental mode?
Yeah, most people's ears are different. So just like people's eyes are different and they appreciate colors differently, people's ears are different and we interpret sounds differently. But mostly, if you give enough elements of a harmonic series, the brain will imagine the fundamental is there, even if it's missing. So that the people I've tested it on have all agreed that they hear bah, that note, which is the one that was actually missing from the series that I played.
Okay, thank you. Why use MRI to study music? Any new information we can measure using MRI?
Oh, that's a great question. So I'm interested in using MRI to measure material properties, and I'm interested in measuring flow with MRI. So the fact that Amy and I used a recorder at that point was rather incidental. What we were doing was developing a new technique that measures faster flows than MRI can usually do, and the recorder was a nice place to demonstrate it. I don't think in that experiment that we learned anything new about recorder playing. But we did learn something new about the MRI technique. We learned something new about the rate at which we can measure gas flows. So Amy has got, in her PhD, Amy went on to use those measurements and develop them for studying turbulence. So we were particularly interested in measuring turbulent, what we call a turbulent eddy diffusivity, which is something to do with the directions of the fluctuations of the flow in a turbulent flow. And the recorder measurements were kind of the starting point for the development of that measurement system.
Perfect. Can you expand on how opening and closing holes in a recorder changes the length of the tube?
Absolutely, yes. So basically, when you've got an open hole like this one, that will be a pressure, let me get this the right way around, that will be a pressure node. So there won't be any fluctuation of pressure there because it's open to the atmosphere. As I close that down, the pressure node is now further along the tube. And as I close that down, the pressure node is further along the tube. So each time I close a hole, I effectively make the tube longer. It's as if the open end of the tube is the next hole down. So now the tube is shorter and shorter and shorter. So you can think about this end of the tube as being closed, and this end of the tube where the hole is being open because the hole is open. And so that determines the wavelength of the resonant frequency. It determines the wavelength of the standing wave that's trapped inside the tube just by changing the length of the tube. I hope that makes sense.
Perfect, thank you. Does having a pipe next to an oscillating string filter out frequencies that are not common to both, or does it somehow amplify common modes?
The latter. So if you've got a string oscillating with a certain frequency and it sets some air moving, that would be a vibration mechanism that gets the air moving in the column. So some of those frequencies are amplified because you get a bigger volume of air moving back and forth at the frequency that you're hearing. And most musical instruments have something called a resonator. The kalimba, for instance, has got this box attached to it. So the idea of the box is it gets a bigger volume of air moving. So you hear a louder sound from each of the keys than you would if this wasn't here. It's the same with the marimba. The hanging tubes get a bigger volume of air moving at the particular frequency. So what happens with the string close to the tube is that any vibrations of the string that happen to be the right frequency to get the air resonating are amplified by the extra motion of the air in the tube. Yeah, good point.
Perfect, thank you. And I think this will be our last question. What impact does gas viscosity have on musical timbre?
Ooh, I think the viscosity has a smaller effect than the density. The viscosity, it makes a difference to the Reynolds number, but it doesn't make all that much difference to the speed of sound in the medium. So the speed of sound in the medium a gas, for instance, depends on two things: the bulk compressibility, that's how squishy the gas is, and the density of the gas. And so as you change the speed of sound, and people might have seen this effect if you breathe in the helium and talk, your voice sounds very high. That's because the velocity of the sound wave in the helium is much different than the velocity of the sound wave in air. And that's, the viscosity is different between helium and air, but that has a much smaller effect on the acoustics than the change in the bulk compressibility and the density of the two. And in fact, the SF6 that we used inside the recorder plays a different note than if you play the recorder with air, but it does that mostly because of the density, not because of the viscosity. I'd have to think about the viscosity question. I don't think it's a very big effect. I don't think it's a very big effect, but because viscosities in gases are so low. But that's interesting. Thank you.
Fascinating, thank you. And we will be wrapping it up now, but I encourage people to stick around.
I'd like to thank Ben by giving him a big clap. Well, maybe he heard that, I'm not sure, but I really enjoyed your talk. Thanks, Ben.
All right. As I said before, I'm Ella Malloy, the CAPS program coordinator. At this time, I would like to thank the regional and national coordinators, our host, Dr. Karen Kavanaugh, for helping organize today's talk. Thank you again to Dr. Ben Newling for an excellent presentation. And thank you all for participating and your fantastic questions. Thank you to the CAP Foundation and its generous donors who have made the CAP lecture tour possible. Please consider making a charitable donation today to support this program and many others. I strongly encourage you to also attend CAP Congress to be held May 26th to 31st at Western University in London, Ontario. The next talk will be by Professor Anya Kwiatkowski on Tuesday, March 12th, 2024 at 12:30 Eastern Time, who will speak on It's a Trap, What One Trapped Ion Can Tell Us About the Universe. I hope you can attend. As a reminder, all participants are now invited to remain to have an informal discussion with Dr. Newling, and you may unmute yourselves and turn on your video. Have a great day, and thank you.
Karen.
Yes, thank you, Ellen. Wonderful. Very